This is 15.2 music. We're going to talk about harmonics, fundamental frequency, and consonance and dissonance. We'll start with air columns. Any of the instruments that you need to blow through, like a clarinet or a flute or a trumpet or even like an organ, that takes air, goes through it, is an air column. When you blow into it, your mouth makes lots of different frequencies, especially like with the trumpet, it has different frequencies. And the different frequencies, well, they'll all go through the air column. But you change the note on the air column, changing its length, and only the frequency that resonates, that fits within that air column, is going to come out of your instrument. So you have lots of different frequencies, and then you pick the one that you want to hear by pushing down that key. And usually the longer that you make that instrument, like on a clarinet, if you put all your fingers down, you can get a very low note. So usually the longer it is, the lower the lower notes you can play. We can do this with a tuning fork and tube. So I have lots of different tuning forks up here, and you'll get to play with these tomorrow. When you use the tuning forks, though, do not bang them on the edge of the table, because that chips them, and that's going to change their frequency. It'll also bend them, which will change their frequency as well. So if you look at this one, it's got lots of chips on the edge of it. That's no good. These things are spinny. In order to activate them, you can use the tuning fork activator, but I only have one of them. Or you can use the bottom of your shoe, or I have these little drumstick things you can use. Now you don't have to hit it so loud that you can really hear it when you're doing the experiment together. All it has to do is vibrate, yes.
Does that mean you're doing it really loud?
Tomorrow, yes. So you can hit it. And then you have your tube. Now this bucket is full of water. And all I'm going to do is I'm going to put the tuning fork above it, and I'm going to lift it until I hear it resonate. And you'll hear what that sounds like if you guys are all quiet. So right there, that's the resonating length. So this length from the top of the tube to the bottom of the water is the length that this frequency fits in. And that means that it will become very loud. Whereas if I put it here, can't hear anything. Put it up here, can't hear anything. But when I find that sweet spot, it becomes very loud. That's the resonance length of this tube. So that's what's happening when you play those instruments, is that you change your keys, and the frequency that fits within that length is going to be the one that comes out. So even though you're playing all these frequencies, you're only going to hear one. And what's happening here is that I'm changing the length of this tube because the sound is reflecting off the water. And so I can make it longer by lifting it up, or shorter by putting it more into the water, so that it changes the length of the tube. It's much more efficient than cutting the tube every single time in order to get that perfect length. So the tuning fork creates a pressure wave, right? We talked about this yesterday. Creates a pressure wave, so it's vibrating, and when it vibrates towards you, that's a dense, high pressure wave, and then it vibrates away, and that's going to create a low pressure wave, and then you get this dense and low and dense and low over and over again. That's going to hit your ear, and that's what you're going to hear as sound. You can do this with an open pipe, but I have to cut the pipe in order for that to make it work. And I don't have billions and billions of PVC pipe to go around and actually cut. So we have it for each one, which is why I use closed pipes here to water. Very good. Nobody's got cups, so I'm going to move on. Here's kind of what the pressure wave looks like. When it's in a closed tube, you have your pressure wave and it reflects back off. And with your open pipe, you end up with the dense pressure wave that goes through. It's going to keep going through, and what reflects is the low pressure wave. This one isn't too terribly important. I'm not going to test you on it. Harmonics. Harmonics I will be testing you on. Harmonics say that many different frequencies can fit in the same length of tube. So this tube, let's say this tube is half a meter long. Well, actually, it doesn't matter how long it is. Let's say that the longest frequency that I can fit in here, the lowest frequency is like 100 hertz. Well, any multiple of 100 hertz will also fit in this tube. So I can get 200, 300, 400, 500. Because 100 hertz has a full half wavelength in here. So it's like a complete cycle for half. If I do 200 hertz, then I get 2 half cycles. So I get one here and one here. If I do 300 hertz, now I have the third harmonic, so I can fit 3 half waves in here. Do the same thing with the fourth harmonic, then I can fit 4 half waves in here. So your harmonics are just the multiple of the fundamental frequency. And again, the fundamental frequency is the lowest frequency that length of tube can play. And the longer it is, the lower the frequency is. Now for closed tubes, it's a little bit different because they're going to bounce back off the water. So it's going to go down and come back up. And since a full half wave has to go through, if it's going to go down and bounce back up, and that has to be a whole half wave, that means it'll be a quarter of a wavelength long. And I'll give you some equations for this, so don't worry too much. If you want to figure out what the harmonic is, a lot of times it's pretty easy to draw them. So for open tubes, all you have to do is count the number of nodes and subtract 1. For air columns, we'll draw them a little bit differently than the way they're actually supposed to be drawn, just so we can count the nodes. For closed tubes, because it reflects back, you count the number of nodes, multiply by 2, and then subtract 1. Because it's going twice the length that it should. So for your harmonics, we have open, and we have closed. Closed. I don't even know what that was. Try again. All right, so find the harmonic number. It is going to be the number of nodes minus 1. For closed tubes, the harmonic number is going to be twice the number of nodes because it reflects back, minus 1. So by looking at the tube, you can actually figure out what harmonic is being played. All right, in order to calculate the fundamental frequency, which again, fundamental frequency is the lowest frequency that can be played in that tube, that will be your first harmonic. So fundamental frequency is your first harmonic. You're going to use this equation, F1 equals V over 2L. This is for open tubes only. I'm going to give you a closed tube one in a little bit. Closed tubes are pretty much the same, it just reflects back, so it's going to be a little different. Fundamental frequency for open tubes, it's half a wavelength that fits in the pipe. Or air column or instrument. it has to be a multiple of half wavelengths. So the fundamental frequency is only going to be half a wavelength because it's the lowest note. It's the biggest part of the wavelength that you can fit in there. It won't be a third of a wavelength. It won't be a sixth of a wavelength. It will only be half multiples of a half. So you can have a half, one, 1.5. Okay, now to find the next harmonic, all you have to do is multiply it by the harmonic number. So I just changed my equation. If I want the first harmonic, I just put 1 in here. If I want the second, now I just put 2 in there. All you do is multiply it by its fundamental frequency. If you want the third harmonic, 3 times the fundamental frequency. So just adjust your equation a little bit. All right, so let's look at some pictures of waves. This is what I'm talking about when I'm talking, when we say we're counting notes. So this is the first fundamental frequency. You can see half a wavelength here. And notice that the notes are on either end here. So we count upper notes, 2 notes, subtract 1, that's the first harmonic. In this one we have a half and then another half, so we have 1 full wavelength. We have 3 notes, so minus 1 is going to be a second harmonic. Then we have 4 notes, third harmonic, we have a wavelength and a half. And then the last one here, 2 wavelengths, we have 5 notes, this will be the fourth harmonic. And it continues to go up from there. This is what your open tubes are going to act like. They don't really look like this, but that's how you're going to count your notes. So for a closed pipe, it's a little bit different. Because it's reflecting back, you only get a quarter of a wavelength. So here's the first quarter, and then the second quarter gets sent back, so you have a full half wavelength here. That is going to be your fundamental frequency. That will be the first harmonic. With an open pipe, this is how we're going to count it. So we have a node on each end. But this is what's actually happening. You always have a node in the center and an antinode here on the outside air. This is what it would actually look like. But this is what we use in order to count the nodes. It just makes it that much easier. So here is some sine waves. There's a version of this in your book. Open ends. So this is what it actually looks like. But notice how hard it is to count your nodes, because if you shift it over, quarter of a wavelength just to the left, you end up with one more node right here. So that is why we don't really look at this to calculate it. We prefer with the nodes on the outside just because we won't miss a node then. So this is what it actually looks like though. Your first harmonic is going to be half a wavelength. Your second harmonic will be one full wavelength. And your third harmonic will be 1.5 wavelengths. Your closed tube, remember, reflects back. So you end up with a quarter of a wavelength because it reflects back to be half. This one is 1.5. So this one gives you your third. And then this one, your fifth harmonic. Notice that with the open, you have first, second, third harmonic. With the closed, you have first, third, and fifth. So you can only have odd harmonics with this closed pipe stuff. You cannot get even harmonics. Which makes sense because if we were to try to get an even one out of there, you'd have to have 1.5 nodes. This one will never spit out an even number. Okay, again, this one's in your book. You don't really need to write it down. This one, I think, is also in your book, but it's a little bit more confusing. We already covered that stuff, so don't worry about writing that down. Where'd my closed harmonic stuff go? Closed tube stuff. Maybe it's on the next slide. It's not going to tell me. Okay, I'll write it down, and then I'll cover it when it pops up. That's the only difference. It's on one of my slides. It will pop up. Okay, so waves on a string. The tension determines the string's velocity. So the higher the tension, the faster the string is going to vibrate back and forth. The density is also going to affect that. The denser the string, the harder it is for it to move. The frequency will not change its velocity. Only the tension and the density of the string, which they call mass per unit length. So it's not quite density, but it's frequency. With strings, they have nodes on each end, so it's going to act like your open harmonic, acts like your opposite of your open harmonic, but it would be the same equation. So if you wanted to figure out that. And strings tend to move very little airs. They don't sound very loud, which is why all your string instruments have a sounding board behind it. That's that hollow case in your guitar or in your violin. I don't know what happened to my closed tube one. Oh well. All right, your wave qualities. A tuning fork is a beautiful sine wave, right? We have this beautiful, pure sound. It makes a pure note. This is what a tuning fork looks like. If you were to, no, you can't hear that. That's your pure sound. And notice that it's a beautiful sine wave looking thing, cosine wave in this particular one. And then if you were to look at, on an oscilloscope, that's what's dropping these things. If you look at a clarinet, it's got all this lovely scribbly parts, which is known as timbre, tone color, and tone quality. So these are the things that make a clarinet sound like a clarinet. Your voice is going to have its own pattern, which will be different than my voice. which is why they do that voice recognition software stuff, passcode things. That's why. It's because this pattern is specific to you. Okay, so now that we see kind of what the note is going to look like, if you put on several different frequencies at once, they're going to overlap. So when they overlap and they get a nice, beautiful pattern, that is going to be consonance. And it happens when you have frequencies of whole ratio numbers, so like 300 and 600. Or 300, 600, and 900. All of those would sound very good together. If you had 300 and 330 playing, it's not going to be very nice, and that's what we call dissonance. So consonance sounds pleasant to the ear, whole number ratio, and dissonance, which you can barely see here in my picture, is when it's not. So you have 300 and like 333. It just doesn't go well with each other. And you're going to get this horrible noise. You just be like, that's not pleasant. That's what happens when people sing off key. That's why I don't want any of you singing in my class. Okay, so here is more of a dissonance wave. We have two different waves, and you can see they have different frequencies, so they line up in some of the places. So when we add them together, we get a large amplitude because there's constructive interference. And then here, when they overlap, they're completely out of phase. So we end up with a very low amplitude, and this low amplitude is going to cancel each other out. That's your destructive interference. So we get what we call a beat. You can actually look at it. It gets bigger and smaller and bigger and smaller. So let's listen to one of those beats. I have two tuning forks up here. One sounds like this, and one sounds like this. And if I play them together, you hear it clashing with itself. That's a beat. If I change the frequency, I'm going to change the beat. So now it's faster. So the closer it is in frequency, the faster it goes back and forth. And that's when it goes off key. Like people say they're singing off key because they're pretty close, but not quite. So you don't quite hear the back and forth of the beat. All you hear is this like really terrible note. All right, let's try this. Next is resonance. Resonance is when two things play with the same note. Everything has its own natural frequency. So this tuning fork is naturally playing whatever note it's playing. And this one, I can make it match. And if I play this note, the same note that this one normally plays, will actually set it off. So this one causes that one to go off without even touching it. The pressure frequency goes in, the pressure wave goes in and it hits it, and this one naturally rings the same one as that one, and it causes it to go. It starts to increase in amplitude. This is how singers can sing that, I think it's a high F sharp, and get glass to break. So that high F sharp played by the speaker, it's got to be played loud enough. That glass has a natural frequency. It has some sort of heat, so it's naturally vibrating at its own frequency for glass. And if they match, then they're going to have constructive interference, and it's going to continue to add the energy from the sound into that glass until it gets so much energy that it's vibrating all over the place and it breaks. Your microwave works the same way at home. It sends out microwaves, which are electromagnetic waves instead of sound waves, and that causes the water molecules to vibrate more and more, so they heat up, and that's what heats your food. You put a wet rag in the microwave, it'll get hotter faster than a dry rag will, because the microwave is heating up the water molecules in it, not the rag itself. So I have some practices for you. My first practice here says an open pipe has a length of 1.75 meters. What is the fundamental frequency of the pipe, and what's the third and fourth harmonic? So what's this 1.75 meters? Length. And what are we looking for? Fundamental frequency. So the frequency when it's at its first harmonic, it is an open tube. So we use this equation over here. Fundamental frequency, 1. Speed of sound, 343, that's a constant, over 2 times our length, 1.75. What do we get? I think it's 98 or something. 98 hertz. Okay, what is the third harmonic? And what is the fourth harmonic? Alright, next one I want you to do is the closed pipe. Closed pipe says it has a fundamental frequency of 95 hertz. What is the length of the pipe? And what is the frequency of the third and fourth harmonic? So what's the 95 hertz? Fundamental frequency. What are we looking for? The length and the third and fourth harmonic. Now this is a closed pipe. Let's use our equation. We have the fundamental frequency times our speed of sound over 4L. Rearrange here. Fundamental frequency, I forgot to put that in there. It's going to be 95. So it would be L equals 343 over 4 times 95. And I get 0.903 meters. We want the third harmonic, 3 times 95. 285. What is the fourth harmonic? What is it? Nope. You can't get a fourth harmonic because it's closed. So there is none. That is going to be a trick on your test. Make sure you pay attention to that. If it says closed and it says an even number, it can't be any of them. So look out for that. That is on your test. And it will get you. All right, I have 3 clicker questions for you. Here's the first one. When an air column and a tuning fork are in resonance, what is heard? Or happening? All right, so here we go. When an air column and a tuning fork are in resonance, you should hear a maximum sound. That's when you could actually hear it from the tube. It's very loud. Question 2, what factors affect the speed of a wave on a string?